The Operator Log, Episode 9. What we've learned. The mechanics of failure. 3 things that break in autonomous systems. Building for autonomy means building for failure. The question is not whether your system will break, it is whether it will break safely. Last week, we covered why Arco publishes its operational decisions in public, why transparency is pre-acquisition documentation rather than brand strategy. The preview at the end of that episode promised something more operational this week. What actually breaks in autonomous systems and how the architecture is designed to handle it. Most agentic AI pitches skip this subject entirely. They describe agentic systems as self-correcting, reliable, and seamless by design. Operators know otherwise. Building for autonomy means building for failure. The question is not whether your system will break, it is whether it will break safely. An autonomous loop that has never failed in production has never been deployed at scale. At Arco, we do not aim for systems that never break. We build systems that fail deterministically. Where the failure mode is known, the recovery is engineered, and MTTI is measured precisely because intervention, when it comes, is the signal that the architecture needs updating. If you have not seen an autonomous loop collapse, you have not built one. What follows is a precise account of how they do. This is the operator log. A human-run business fails through mechanisms that are visible and attributable. A bad hire makes a poor judgment call. A deadline is missed because a team was understaffed. A decision is made on incomplete information, and the consequences surface when the next data point arrives. Each of these failures has an author. The failure is traceable to a person, a moment, and a set of circumstances. It can be managed through the same supervision mechanisms the business already has: a review, a correction, a process change, a conversation. An autonomous business fails through architectural mechanisms. These are different in kind, not just in scale. Logic that was correctly calibrated for one data environment produces incorrect outputs when the environment shifts. An agent executing a long multi-step workflow loses the intent of the original task across 30 sequential operations without any single step flagging an error. An integration point between two systems returns an unexpected schema, and the agent, finding no clean resolution, produces a plausible-looking fix that propagates through the downstream workflow as if it were correct data. None of these failures have a visible author. None of them announce themselves the way a human error does. They compound quietly, sometimes for hours, sometimes for days, before the accumulated drift becomes impossible to ignore. This difference matters for design. A business built to be managed by humans can tolerate occasional human error and course correct through supervision. The supervision layer is always present. A business built for architectural certainty cannot defer to supervision as a recovery mechanism, because the point of architectural certainty is that the system runs for days without requiring the steward to intervene. If supervision is the primary recovery mechanism, MTTI cannot exceed 72 hours. The design target collapses. The implication is precise. Every failure mode in an autonomous business must be anticipated before it occurs, handled by the system when it occurs, and logged with sufficient precision that the steward can diagnose and resolve the architectural cause after it occurs. The steward's role in a failure event is not operational firefighting. It is architectural improvement, identifying which logic gate produced the deviation, updating the system so the same failure class does not recur, and expanding the system's authority in the tiers where the updated architecture has now proven stable. The measure of a well-functioning MTTI is not that the steward is never needed. It is that the steward is needed less often after each intervention. A system that fails silently and non-deterministically cannot be improved. Because the failure cannot be reliably reproduced, the cause cannot be precisely identified, and the fix cannot be validated. A system that fails deterministically, predictably, logged, with a defined recovery protocol, can be improved with every failure it encounters. Deterministic failure is not a concession to imperfection. It is the engineering discipline that makes an autonomous system trustworthy over time. Arco documents these failure modes not because transparency is a marketing virtue, but because a system you cannot describe precisely is a system you cannot fix. What follows are the three failure modes that every autonomous build encounters at scale, the mechanism that produces each one, and the architectural response Arco has developed for each. The first failure mode is context leakage. It is the primary failure in long-running agentic workflows and the hardest one to catch before it causes damage, because the agent has not broken. It has drifted. Context leakage occurs when an agent loses the intent of the original task as it progresses through a multi-step process. The agent continues executing, fetching data, reconciling records, updating systems, but the accumulated effect of small errors at each step produces a result that is technically compliant with the instructions and logically irrelevant to the goal. Each individual step looks correct. The cumulative outcome is wrong. The agent has executed the workflow successfully and produced an output that no one designed it to produce. To make this concrete, consider an agent processing a high-volume intake queue, classifying documents, extracting key fields, routing each item to the correct downstream workflow. In step 12 of a 30-step process, a classification decision is made with marginally lower confidence than the threshold that should have triggered an escalation. The agent continues. Steps 13 through 30 execute correctly against the wrong classification. The output is routed to the wrong workflow, processed by the wrong rules, and closed with the wrong outcome, without a single step along the way generating an error flag. The agent did exactly what it was told. It just lost the thread of what it was supposed to be doing. This is the agentic equivalent of an organization that executes every individual task correctly but loses sight of the strategic objective across a long chain of handoffs. The T-tier framework from episode 1 helps explain why. Context leakage is most dangerous in Tier 2 workflows, conditional reasoning within defined constraints, where the agent has the most latitude and the deviation from intent is the hardest to detect at the individual step level. Arco manages context leakage through an execution divergence threshold. If an agentic workflow deviates by more than 15% from its predicted path or confidence interval at any point in the chain, the system triggers an automatic rollback to the last known good state. The workflow halts. The steward is notified with full context, the step at which the divergence occurred, the confidence score that triggered the threshold, and the accumulated deviation across prior steps. The logic is reviewed and updated before the workflow resumes. Handoff friction is the failure mode most often inherited from the incumbent architecture rather than generated by the agentic system itself. This is precisely the legacy liability problem we identified in episode 6. Operating at the micro level, systems designed for human interpretation accumulate ambiguity that the humans can navigate through judgment and context, but that agentic systems cannot safely process. A legacy API that returns inconsistent schemas depending on which version of a record it is querying is a manageable inconvenience for a human coordinator who knows to check. It is a structural risk for an agent that cannot know what it does not know. Arco handles handoff friction by building a machine-readable interface at every integration point. A machine-readable interface is a structured, schema-validated layer that enforces strict data contracts between systems. An agent operating through an MRI cannot guess. The schema is either satisfied or the handoff fails cleanly. The exception is surfaced, the steward is notified, and the workflow holds at the exact integration point that generated the failure. For integration points with legacy third-party systems that Arco cannot redesign, we build adapter layers that translate between the external systems format and the MRI schema, with explicit failure handling when the translation cannot be completed cleanly. Every external integration is treated as potentially unreliable. Every data point is validated before it touches the agentic workflow. The third failure mode is logic decay. It is the most insidious of the three because it is invisible until it produces an error that is impossible to miss, by which point the error has often been compounding for weeks. Logic decay occurs when the underlying data environment shifts and the logic calibrated for the previous environment continues to execute against the new one. The code is not wrong. The prompt is not incorrect. The agent is not broken. The world the architecture was calibrated for has changed, and the architecture has not been updated to match. A logistics pricing model calibrated on first quarter fuel cost data is not buggy in the third quarter. It is miscalibrated. Each individual output is plausible. The accumulated pricing error across thousands of transactions is not. This is what distinguishes logic decay from a standard software bug. A software bug is a defect introduced during development, present from deployment, discoverable through testing. Logic decay is a calibration problem introduced by environmental change after deployment. No amount of pre-launch testing would have caught it, because it did not exist at launch. It emerged as the gap between the world the logic was built for and the world it is currently operating in, widened past the point where the outputs remained within acceptable parameters. The conditions that produce logic decay are common in any live business. Customer behavior shifts as the market matures. Pricing adjusts in response to external factors. A supplier API updates its data schema in a minor version release that changes the distribution of a field the logic was using as a classification signal. A regulatory threshold is updated. The season changes and the base rates for a time-sensitive service move outside the range the model was trained on. None of these changes is dramatic. None generates an immediate error. Each nudges the logic's outputs slightly further from correct, and the drift accumulates silently until someone notices the pattern, or, more often, until the pattern produces an output that is impossible to explain away. Arco implements continuous regression loops to detect logic decay before it reaches the revenue loop. A continuous regression loop runs ghost trials, simulated production data constructed to reflect current environmental parameters, through the live logic in parallel with the real operations. The ghost trials are not historical data replays. They are constructed to probe the current logic against the range of inputs it is likely to encounter under current conditions. When ghost trial outputs diverge from expected parameters, the system flags the drift before any real transaction is affected. The logic is reviewed and recalibrated. The steward receives a notification identifying which component of the logic produced the divergence and by what margin. Most firms ignore logic decay until it produces an error that cannot be attributed to a specific event. By then, the error has been compounding for weeks in outputs that looked individually plausible. The investigation works backward through the output log, trying to identify when the drift began, which environmental shift triggered it, and how many downstream decisions were affected. In an autonomous business operating at scale, that investigation is expensive, time-consuming, and in some cases, structurally inconclusive. The ghost trial protocol converts that investigation into a prospective detection. The drift is caught before it reaches the revenue loop. The cause is already identified, and the fix is applied before a single real transaction is affected. The three failure modes operate at different architectural layers. Context. Leakage is a task-level failure. It lives within a single workflow and concerns whether the agent maintained task intent across the chain of its own steps. Handoff Friction is a system-level failure. It lives at the boundaries between components and concerns whether data passes cleanly between them. Logic decay is an environment-level failure. It lives in the relationship between the logic and the world it is operating in, and concerns whether the calibration that was correct at deployment remains correct under current conditions. Each requires a different detection mechanism. Each requires a different recovery protocol. What they share is the signature of autonomous failure. They do not announce themselves. They compound silently until the agentic core is producing outputs that no longer match the design. The engineering discipline that addresses all three is the same. Build for deterministic failure rather than hoping for the absence of failure. A deterministic failure is one that is predictable, repeatable, and fully logged. When an Arco system encounters a condition outside its defined parameters, the failure follows a defined protocol. The workflow halts, the deviation is logged with full context, the steward is notified, and the system waits for architectural input before resuming. In a non-deterministic system, you discover the failure after it has produced downstream damage and spend engineering time reconstructing what happened. In a deterministic system, the log shows exactly which intervention was required and why. Fixing the business becomes an engineering task, not an investigation. What are the three failure modes in autonomous business systems, and how does Arco handle them? Arco identifies three primary failure modes in autonomous systems. Context, leakage. An agent loses task intent across a multi-step process, managed through an execution divergence threshold that triggers automatic rollback at 15%, deviation from the predicted workflow path. Handoff Friction. Schema mismatches at system integration points cause agents to hallucinate fixes rather than report failures, managed through machine-readable interfaces that enforce strict data contracts at every integration point. Logic decay. Shifting data environments cause calibrated logic to produce incorrect outputs over time, managed through continuous regression loops running ghost trials that detect drift before it reaches the revenue loop. All three are managed for deterministic failure, predictable, logged, recoverable. Key metrics: execution, divergence threshold, 15%, MTT, I target greater than 72 hours. Here is the verdict on failure in autonomous systems. The agentic AI pitches that skip the failure question are not describing a more advanced system. They are describing a system that has not been deployed at scale. Every autonomous loop that runs in production encounters conditions outside its defined parameters. The question is not whether it will. It is whether the failure is deterministic or non-deterministic, predictable and recoverable, or silent and compounding. The rollback protocol for context leakage, the machine-readable interface layer for handoff friction, the continuous regression loop for logic decay, these are not defensive measures added to protect a fragile system. They are the architecture. A system without them is not an autonomous business. It is an autonomous process running without guardrails in an environment that will eventually produce conditions the process was not designed for. An autonomous system that never fails in the log has not been operated honestly. Every failure mode documented in these episodes is evidence that Arco has moved past the hype phase and into the operational one. Sophisticated investors and acquirers understand this. A precisely documented failure record is more credible than a suspiciously clean success record, because it is proof that the system has been stress-tested in production, not just demonstrated in a controlled environment. The full written version of this argument, including the precise definition of each failure mode and the detection mechanisms, is memo number 9, The Mechanics of Failure, on the blog at arcoventure.studio. The Arco lexicon at arcoventure.studio/lexicon defines machine-readable interface, MTTI, and the other architectural terms introduced across the 9-episode arc. Next week, the stewardship model in full, the human role in an autonomous business, what the steward actually does when the architecture is holding, and what the role becomes when it is not. We seeded this term in episode 2. Episode 10 delivers the full argument. Trust in an agentic system is not built on hope. It is built on the certainty that when the system fails, it fails safely. This has been episode 9 of the Operator Log.